If you're taking physics for the first time, it can look like a giant collection of equations, and somehow you're supposed to know exactly what to do and when to do it. But that's really not what physics is. Physics is about taking something happening in the real world, describing it using math, and using that description to predict what's going to happen next. And throughout this course, I'm going to focus not just on solving problems, but on recognizing what kind of problem you're looking at and why a particular method is better than another one. Let's start with probably the simplest physical system imaginable. We have an object and it's moving. First, I can describe where it is. But position alone doesn't tell me what's happening. I might also want to know how quickly it's changing. This would be the velocity. And then I can ask, how quickly is this velocity changing? This would be the acceleration. So now we have three different properties that can describe an object. We have the position that says where it is. From there you have the velocity, which says how quickly the position is changing. And then you have the acceleration, which says how quickly the velocity is changing. Units aren't just some decoration that we put at the end of an answer. You can actually use them for problem solving to make sure your answer makes sense. Say that you have velocity, which is the change in position over the change in time. Well, the units for position or length is meters. And the units for time is seconds. So that means the units for velocity are meters per second. And anytime you see brackets like this, that means you're finding the units of it, you're not finding the actual answer. Well, let's do the same thing for acceleration, which is the change in velocity over the change in time. Well, the units of velocity we just found are meters a second, and then the units of time are seconds. So then the units of acceleration are meters per second squared. Say that I tell you the position is velocity plus time. The units of position are meters, the units of velocity are meters per second, and then the units of time are seconds. Well, then this expression would be wrong. We're saying that meters is meters per second plus seconds. That doesn't make sense. So if you ended up with the answer where the units don't match what you were expecting, then that means your answer is wrong, and you probably need to go back and see where you messed up. If I tell you something has moved 5 meters, have I completely described its motion? No. So that would just be a scalar. If I said something moved 5 meters to the east, then that would be a vector. So a scalar is just magnitude, and a vector is magnitude plus direction. Some examples of scalars would be mass, time, temperature, and energy. Some examples of some vectors could be displacement, velocity, acceleration, and force. Say that I have this velocity vector here in green. In order for it to be useful to us, we need to know its components. And by that I mean what portions in the x and y directions are contributing to this vector. So anything vertically would be the vertical component of this velocity, and anything horizontally would be the x component of this velocity. So if we wanted to write our velocity vector, we would write it like this. Where x hat and y hat here just mean in the x and y direction respectively. Breaking vectors into components like this is going to be one of the most common things we do in this entire course. So in a separate video, I'll go over how to do that. Let's go back to this object moving example. Instead of looking at the object itself, we can graph its position over time. And if we take the slope of this line between the 2 points, where the slope is just rise over run, we have rise, which is the change in position, divided by the change in time, or the run. And if you remember, this is our velocity equation. So the change in position over time is the velocity. If you're taking physics with calculus, then you would see the velocity written like this, where this is the derivative notation. But if you're taking algebra-based physics, you don't have to worry about that. The physical idea is the same. The velocity tells us how quickly the position changes. And then to find the acceleration again, that's how quickly the velocity changes. Or if you were in the calculus-based physics, you would see it written in derivative notation. So we have this relationship between position, velocity, and acceleration, where acceleration is the rate of change of velocity, and velocity is the rate of change of position. Here's an example. This object here has a velocity of -5 meters a second. Is it slowing down? The answer is we don't know. From this picture and what it tells us, we only know the velocity. We don't know how the velocity changes over time, so we don't know if it's accelerating or if it's decelerating. Say you have a velocity of -5 meters a second, but then you also have an acceleration of -2 meters a second squared. Since your velocity and acceleration are in the same direction, or they're both negative, that means your speed is increasing. What if the velocity was still -5 meters a second, but in this case the acceleration was +2 meters a second squared? Since their signs or their directions are opposite, now the speed is decreasing. So if velocity and acceleration have the same sign, if they're both positive or if they're both negative, then speed is increasing. If velocity is positive and acceleration is negative, or if velocity is negative and acceleration is positive, then the speed is decreasing. And the speed is the magnitude of the velocity. So you can have a negative velocity, the magnitude would still be the number, the negative sign would be the direction. We've described motion, but what actually causes velocity to change? The answer is force. The net force is equal to the mass times the acceleration. This is what's called a free body diagram. And in a later video, I'll go into detail about these. But essentially, it just describes all of the forces acting on an object. So on our object that we have moving, so there's a normal force, which is the resistive force of the ground, which the block is on. There's the gravitational force, which is mass times gravity pulling the object down. And then there's the applied force. In this case, it would be pulling the block if the arrow was on the other side pushing the block, but it's just a force that's being applied causing the block to move. So when you add up all of these forces, you can solve this equation. The important word here is net. An object can have multiple forces acting on it, but what determines its acceleration is their vector sum. So once you've summed all of these force vectors together, you can solve for the acceleration. And like I mentioned earlier, once you have the acceleration, you know that the acceleration is the change in velocity over the change in time. So then you could solve for the velocity. And once you have the velocity, you can solve for the position. So forces determine the acceleration determines the velocity, and then the velocity determines the position. This is the workflow of a ton of physics problems. Is you figure out the forces, from that you can get the acceleration, and then from that you can figure out equations of motion that describe how the block would move over time. But an interesting thing about physics is there's often more than one way to attack a system. Say that we have this ball and it's a distance h off the ground. At the top, the potential energy of this ball is mass times gravity times height. If you drop this ball and once it reaches the bottom, the kinetic energy is 1/2 mv squared, where m is mass and v is velocity. So this ball initially starts with purely potential energy, since it's not moving, so there's no velocity. Once it reaches the bottom, the height is 0, so there's no potential and it's purely kinetic energy. So in this system, you have this trade-off of potential and kinetic energy. The total energy, or the mechanical energy, will be the sum of the kinetic energy and the potential energy. So with forces, we could describe what's happening moment by moment, but sometimes we don't actually care about everything in between. We only care about what happens at the beginning and at the end, which is when energy would be a more useful tool. And something really cool about energy is that it's conserved. So the total energy in the beginning, or the initial energy, is always going to be equal to the total energy at the end, or the final energy. So in the case of this ball, that would be mass, gravity, height is equal to 1/2 mass velocity squared. So if we were given the height, if we were given the mass, and we knew gravity, we could solve this equation to find the velocity of the ball. Here are some patterns that might help you. Don't always automatically start with F equals ma. If there's motion, then usually it's a kinematics problem. If there's forces, then you're probably going to want to use Newton's laws. And then if it gives you the initial or final states, then you'll probably want to use energy or conservation of energy. So a big part of physics is this decision making. You're given a problem, there's multiple ways to solve it, so which of the ways is the best and most efficient approach? Here are the 7 steps that I use anytime I approach a physics problem. First, draw the situation. Then, choose a coordinate system. Third, you write what you know. And by that, I mean whether it's something the problem tells you explicitly, like if it says the block starts at 12 meters a second, or it's something you know implicitly, like you know gravity is always going to be 9.8 on Earth. Then you want to identify what you need. There could be a ton of things that you can solve for, but that doesn't mean it's going to be useful. So by determining what you need, you'll stay on track and not waste any time. Then you want to identify the physics. And this is the most important step. This is where you decide if you're going to use kinematics, if you're going to use Newton's laws, if you're going to use energy. This is the step where you determine the right approach by identifying the patterns that the problem is telling you. Then you solve the problem. And finally, check your work, check your answer. Whether that's by working backwards, or you could check the units, like I mentioned in the beginning of the video. Let's do an example. A car is moving at 5 meters a second and it accelerates at 2 meters a second squared for 3 seconds. It wants to know the final velocity of the car. So let's do it step by step. First, what I always do is I draw the situation. You don't gotta do any fancy drawings. I'm a physicist, not an artist. So this block is the car. It's moving at 5 meters a second. And then we want to choose our coordinate system. This is pretty simple. We'll just say anywhere to the right of this car is positive x. This keeps things simple so we don't have to worry about negative signs. Then we write what we know. We know the initial velocity is 5 meters a second. We know the acceleration is 2 meters a second squared. And we know the time is 3 seconds. Step 4, identify what we need to know, the final velocity. That's what the question asks for, and that's the only thing we need to solve for. Step 5 is the hardest step. What kind of information did they give us? They told us velocity, acceleration, time. So this would be a kinematics problem. I'm going to upload a video just on kinematics for this course, but one of the kinematics equations is the final velocity is equal to the initial velocity plus acceleration times time. So now we can do step 6 where we can just solve the problem. We know initial velocity, which is 5. We know the acceleration, which is 2. And we know the time, which is 3. So the final velocity is 11 meters per second. Now the final step is checking. The units of this kinematic equation are meters per second for the final velocity is equal to meters per second plus acceleration, meters per second squared, times time, which is just seconds. So one of the seconds in the denominator here cancels out. So we're left with meters per second is equal to meters per second. So the units here check out. And what about in our answer? The units of our answer were just meters per second. And we can also think about if our answer makes sense. We started at 5 meters a second, and then it ended at 11 meters a second, which makes sense because the car is accelerating, so the final velocity is going to be greater than the initial velocity. Here's our roadmap for the course. We're going to start by learning how to describe motion. Then we're going to learn what causes that motion to change, which is forces. From there, we can develop the conservation of energy laws. We can study collisions and rotation. And eventually see how the same ideas describe oscillation and orbital motion or gravity. But throughout all of it, I want you asking the same question. What information did the problem give me, and what physics connects that information to what I'm trying to find? So in the next video, we're going to build kinematics from the ground up, and you'll learn how to recognize each major type of motion problem.